Okay, so now it's time for David. We will tell new results.
Good afternoon, everybody. This is some new results that we've obtained. The collaborators are, oops, it's a tricky pointer, Andrea Paradi, Mohammed Zorania from Antwerp, and Francois Peters from Antwerp. And it's extending our previous work on bilayer graphene to few layer graphene, by which we mean bilayer, tri-layer, quad layer, and I'll explain the motivation for that almost immediately. Thanks to all the previous speakers, I can flick through these first slides very quickly. I do want to acknowledge the pioneering work of Yuri Lojovic, and I've already expressed my great regret that he was not able to get a visa to give the plenary talk this morning. Some years ago now, Alan and co-workers made the proposal that double monolayer graphene would be an excellent candidate for seeing high temperature superfluidity. In fact, their title was included the word room temperature superfluidity, and the idea behind it is the coupling of the electrons and holes is coulombic. That's nice and strong and should lead to large energy scales. I can skip this slide almost immediately. This is the difficulty with monolayer graphene, that the parameter Rs, which determines the ratio of the kinetic energy to the potential energy, cannot be varied in monolayer graphene because of the linear dispersion. And we proposed to get around this problem a system in which the monolayer graphene was replaced by bilayer graphene. The trick there is that with bilayer graphene at low energies, the dispersion is quadratic, and therefore the RS parameter has a density dependence, and you can get to large RS. Just very quickly acknowledging that if we could get this system, which has been searched for now for how many years? Is it 40 years? My maths is not very good. 75 to 2014. Is that 40? Yes. 40 years. Yeah. It's been real soon now for as long as I can remember. And so there would be some nice applications, particularly if the temperatures could be high. And Alan mentioned another motivation for that. Okay, this talk is an extension of this, and I acknowledge Francois Peters had the original idea of this, to extend from bilayer to few layer graphene with the idea of exploiting the faster dispersion when you go to tri-layer and quad layer. So our system consists of two gates, which are actually important for another reason apart from controlling the density of the carriers. Then we have few layer graphene. We have a very thin insulating barrier, as Alex explained. You can do that. Maybe 3 layers of HBN are sufficient to keep the electrons and holes apart. A second few layer graphene, and then a back gate. And so this just lists it again. 2 few layer graphene sheets separated by nanothin HBN insulating layer. Within each sheet, the fixed stack layer separation is very much less than the effective Bohr radius. So we can consider the individual sheets as strongly coupled and hybridized. And then just simply the upper sheet contains holes, the lower sheet contains electrons, and we can nicely balance them and so on using the gates. And so the idea behind this is very simple, but it's a nice idea. And that is that the dispersion depends on the number of layers. I'm going to use n always as the number of layers in the sheet. So bilayer n equals 2, tri-layer n equals 3, quad layer n equals 4, and you have some constants here times k to the n. So for bilayer, this would be the familiar quadratic dispersion. And you see, with the appropriate numbers for graphene, our co-worker at Antwerp, Mohammed Zorania, knows graphene the details of graphene like I know this part of my hand. And so he knows all the numbers very well, and so he put in the numbers. And these are the resulting dispersions. So the RS then, as we change the number of layers, you can see that when n equals 1, RS is fixed. So for monolayer, RS is a fixed number independent of density. Sorry, the density is here. The n here is the density. So n equals 1, RS is independent of density. N equals 2, you get the familiar 1 over square root dependence of density. But then as we go up with the number of layers in each sheet, this increases rapidly as the density decreases. We put in some typical densities here. This is the monolayer RS. This is for a kappa of 3. The bilayer, Alex mentioned, you can get up to about RS equals 9 with current bilayer sheets. Tri-layer is looking good, and quad layer is spectacular. And I might add here, we're always looking at superfluidity, but many of us have had a background in strongly correlated electron systems, and there is life outside superfluidity. With these sort of RSs, there are some extremely interesting other physical processes that one could study with these multi-layer sheets. Make the point that you can realize these few-layer graphene sheets. Tri-layer graphene sheets single tri-layer graphene sheets have been successfully fabricated of good quality and so on. And I mentioned also that the separation between the sheets, as Alex emphasized, that separation is really important. You've got to get the electrons and holes real close, but not so close that they touch and recombine. And this is realizable with. There is a little. Leonard tells me there's a little bit of leakage at that level, but it's. Am I right? The pico amp. Many things, but that's about the limit. But we can get to that. So the aim here is to provide experimental indicators for designing systems to look for high TC electron-hole superfluidity. We want to always, as Alex mentioned in his talk, we're always wanting to work with realistic systems, with realistic parameters. And in this work, we once again evaluated the superfluid energy gap within extended mean field. An important point here, that once you go beyond monolayer, bilayer, trilayer, quad layer, almost of necessity you have to have gates to control the densities, but that actually gives you a bonus, because that perpendicular electric field induces an energy band gap. So it tends to make the contributions from the graphene valence band small. And so in what I'm going to present here, we will consider contributions only from the conduction band. However, we have a very active program also involving Arkady Shenenko, and we have included contributions from the valence band, and we confirm that in the results that I'm presenting here, that the contributions from the valence band can safely be neglected because of the band gap. As I said, it's a bonus. The fact that when you have a bilayer, if I have a metal gate here, I'm putting a transverse metal electric field across the bilayer, I get the gap which is not there in the monolayer. And similarly, obviously, the trilayer and quad layer. So this is the Hamiltonian that we use for our calculations, just for a single band. This is the energy of the electrons and holes, shown here with quadratic dispersion, but for the trilayer it goes like k cubed. Then we just did a very standard mean field calculation. We set the electron and hole densities equal, and we set the chemical potentials equal. We're doing a zero temperature calculation here, and our unknowns are the wave vector dependent gap and the chemical potential. And there's nothing surprising there, nothing unfamiliar. The degeneracy is 4, 2 valleys, 2 spins. With the interaction between the electrons and holes, we start with a standard expression in the normal state within the random phase approximation, which is this expression here. D is the separation between the layers. The pi 0 here is simply the two-dimensional Linhart function. In the regions that we're interested in, the momentum transfer where you get appreciable screening is small compared with 1, and this that kills this term here. So this is a good approximation. Essentially, we confirm that you get the same results with this and this using the normal state screening. Have I defined everything else? The VQ is just the Wehr-Coulomb interaction with an appropriate kappa for the dielectric constant. Yes, so everything there is specified. Now we want to consider screening in the presence of superfluidity, and basically what we do is we take this expression and then we replace the Linhart function by the normal and anomalous contributions that Alex referred to, and so the total polarization is the sum of those. These need to be calculated self-consistently, these quantities, because the gap enters in. I mean, the physics of it is that if they're in the presence of superfluidity, you get a gap in the single particle spectrum that tends to kill the low, well, it kills the low energy excitations, which are exactly the ones which you need to screen out long distance screening. So you need to do a self-consistent calculation where you assume a gap, calculate these quantities with that gap, calculate a new gap, and repeat the process. Now I mentioned that we use this approximation for the normal state screening. If you use the full expression, then the expression that we obtain reduces to the full expression, provided the momentum transfer is in that range. And as I mentioned, once you get outside this Q range, the screening becomes unimportant. It's sort of the form 1 over Q squared plus mu squared. If you're interested in the screening, you want the Q to be small so that the mu is important. If Q is large compared with mu squared, you get no contributions. So as Yuri Lozovic pointed out, the energy gap in the excitation spectrum, delta for the superfluid state, suppresses the polarization, pi 0 Q, for small q. And because it suppresses the screening, the Cooper pairing can become strong. And as I said, that's the self-consistent effect. Now, there's been controversy about what to do about screening. There's been 3 schools of thought. Alex referred to this. One school of thought was the best thing to do in the absence of knowing what to do is to use the unscreened interaction between the electrons and holes. Another school of thought says one should use the screening appropriate for the normal state, and the third school argues that you should include self-consistently the gap in the screening. In other words, the screening is aware of the fact that there is a gap in the single particle excitation spectrum. The results from these 3 cases can vary by 6 orders of magnitude. So there are a number of excitable papers in the literature arguing their case. There exist in the literature quantum Monte Carlo results for related systems. I mentioned the early work of Stefano Di Paolo, Gaetano Senatore et al. We calibrated our work against these results here from Richard Needs and a Japanese group. And basically what they did, the results that we calibrated, this is from their paper, condensate fraction for different values of D versus RS. And well, that's interesting. I'm really fascinated about that. Trouble with Wi-Fi.
And now this works for me.
Yeah, okay. Now, key things that they observed. They found that at high density there was no superfluidity, which we interpret that the screening is just too strong to permit a gap to develop. Then there is a discontinuous jump to finite values of the condensate fraction, and after that the condensate fraction increases, approaching 1. 1 would correspond to pure BEC. At larger values of these curves then actually turn over. There's another effect due to the onset of biexcitons, but I don't want to enter into that because it's not relevant for our work. So this is sufficient to calibrate for this, and this is a comparison of the various theories of screening. And Joe, could I just ask, what time did I start? Because I want to have a perfectly timed stop.
At 12:25.
12:25. Okay, so I have about, yes, okay, 10 minutes. So this is the comparison for the condensate fraction. Here D is equal to 0.7. This is the result of the condensate fraction for no screening. The condensate fraction here actually goes exponentially to 0. There is no onset density. These are the DQMC results. These are our results, screening in the superfluid state. This is screening in the normal state. Now this figure differs slightly from our published result because we misread the definition of RS in Richard Need's paper, and we inserted a square root of 2 in there, which I am indebted to Gaetano Senatore and Stefania Di Paola for pointing out that that square root of 2 was in fact not there. It was as simple as what their definition of density was, and it's a little bit annoying, but it actually doesn't change any of our conclusions. When we reported, our agreement was somewhat more spectacular. There was a fact, as I said, this moved back by a square root of 2, but our purpose on this is not to obtain perfect agreement with DQMC, but to say, if we predict superfluidity, then is that prediction reliable? And in fact, what this is telling us is that our definition or our approximation is on the pessimistic side. So the conclusion is, we believe from this, and that's all we need from these results, the conclusion is that you should use screening if you use screening in the superfluid state, which is the most appropriate approximation, and if you predict superfluidity, then it really is there. We may miss out in a range where there is superfluidity and we predict that there is not, but we are on the pessimistic side. This compares the onset of the superfluidity in the DQMC and screening in the superfluid state. You do not see the other two curves because they do not have an onset density. The condensate fraction goes exponentially to 0, so at arbitrarily large density you get the superfluidity. This, in order to compare the three approximations, this is for a fixed condensate fraction of 0.25. This is D, the spacing between the separation between the sheets. This is screening in the superfluid state, no screening, and screening in the normal state. So based on those results, we conclude that the agreement between our mean field calculation with screening and DQMC indicates that screening should be calculated in the presence of superfluidity, and it is on the pessimistic side. In other words, if we predict superfluidity, that's a very reliable prediction. Okay, let's now apply, that was just calibration. That was calibration actually for two quadratically dispersing sheets. Purely a calibration. Now we talk about the system in which we're currently interested, new results for double few layer graphene. First point here is to note that the density of states really helps us. When n is greater than 2, there's a Van Hove power law singularity in the density of states. So in the density range in which we are interested in, the density of states for n equals 3 and n equals 4, you do need thin fingers for this. I noticed a number of speakers have had this trouble. I'm now having the same difficulty. For n equals 3 and n equals 4, there's in the range, relevant range of densities, there is a big boost in the density of states. These are the results for the gap. In the case for bilayer, tri-layer and quad layer, D is equal to 2 nanometers in this result. The other point that I want to make here, apart from the notable boost in the gap as you increase the number of layers, is to make the point, I've got a code here, where the lines are solid, that's a BEC region. I'll give you the criterion in a moment. This region here is the crossover region. And the BCS region is, it's not there. What happens is the screening kills the superfluidity before you get to the BCS. So above these densities here, above these onset densities, if there is any superfluidity at all, the gap would be exceedingly small, much less than 1 Kelvin, and in realistic systems with any disorder, unlikely to be there at all. And then at the onset density, there's this sudden characteristic, discontinuous jump in the gap. This is a criterion we used.
Why the F is smaller than in the talk value? Because now the scale is in n equal to 2, the maximum is in 100 Kelvin. Here the 400 Kelvin. Because of D, this larger.
Yeah.
This larger.
2 nanometers is
Yeah.
different D.
Different D. Yeah. This is our criterion for the different regions, BEC, BCS crossover, and BCS. We use the condensate fraction as our criterion. So the most important effect of screening is to suppress the superfluidity at large densities. If I do this calculation without screening, what it looks like, the gap is somewhat bigger in this region, maybe a factor of 2, but then it just continues like this. So the screening kills the gap at high density. If you don't have screening, you get a large gap. You get a dramatically different result. Another very interesting thing is that in the BEC regime, the solid lines here, the effective screening is weak. The screening is weak in the BEC regime because the electron-hole pairs are compact. And we keep hearing that there's been a common theme. I enjoyed the previous talk on this. In fact, even the RSs are consistent with that. If we take the peak in the delta max here, it's the largest value of delta K, that's already in the BEC region. If I redo this calculation, in the unscreened case, the difference is about a factor of 2. In other words, not dramatic. So what the screening does, it kills the superfluidity at high density. That's all it does. In the neighborhood of the peak of these, the vector screening is to reduce delta by a factor of about 2 compared with the delta without screening. This gives you the densities for the onset of the superfluidity as a function of the number of layers. And you can so this is the separation between the sheets, and this is the onset density. And it is notable that if you go from bilayer to quad layer, you're getting a boost in the onset density of a factor of 10. It's a dramatic effect. So notable increase in the onset density of the number of layers. In fact, for the quad layer, you can get up to 10 to the 12 centimeter minus 2.
3 minutes before
3 minutes, okay. And clearly, it's an advantage to work at higher densities because the effects of disorder are smaller. I'll move very quickly through the temperature because Alex gave an excellent introduction to the fact that we use the Cosford-Stalis as the criterion for the transition temperature. Just make the comment though that you do need a large value of delta resulting from strong pairing before you can hope to get a high transition temperature. And one other comment, that when one is calculating the superfluid density, this thing only is proportional to n in the case of bilayer. If you go to tri-layer and quad layer, you lose this proportionality. So this is the maximum transition temperatures from Cosford-Stalis. Always occurs at the maximum density for the superfluidity. We are careful to present results only when TKT is much less than the maximum value of the gap. which brings me to the to my conclusions, which is increasing the number of graphene layers in each sheet greatly enhances the density of states, thanks to Van Hoek, and this projects the sheets into the strongly interacting regime, leading to strong electron-hole pairing at accessible densities. If we increase the number of layers in each sheet from bilayer to quad layer, we double the transition temperature, everything else being equal, and we increase the onset density actually by an order of magnitude. Very dramatic effect. The electron-hole superfluidity is predicted up to, we get up to about 60 Kelvin with this. So close to liquid nitrogen. Densities, as I mentioned, in the quad could be as high as 10 to the 12. All the experimental parameters with which we've been working have been already attained in related graphene systems. And that leads me then to my exciting conclusion. It suggests we really are really close now. That suggests electron-hole superfluidity and counterflow superconductivity should be detectable using current technology.
Thank you very much, David. We are having some questions. 2 or 3 questions. Yes, Gaetano, please.
I have a small problem with your definition of RS. As far as I understand, you take the ratio between the average potential energy at the average distance between particles to the Fermi energy.
Our RS, in what I presented there and what we presented in our papers, with the exception of the calibration issue, which is with needs, with the exception of that, our RS is defined in a standard way in terms of the electron effective mass.
That's not the problem.
Mm.
I repeat it. I just checked on the paper. As far as I understand, and this is consistent also with previous papers, you take the ratio between the average potential energy, which is this square divided the average distance between the particles, okay, the electrons or whatever, ratio of this to the Fermi energy, okay, which involves putting factors that come in Fermi energy, which is a non-interacting concept.
Well, yeah, all I can say, I mean, I think you asked me what my definition of RS was. I can say what, this thing may be interpretable in terms of ratios of kinetic energy and potential energy. But the important thing as far as communicating what one is calculated is what is our definition of RS. And I repeat, our definition of RS, with the one exception of the... I can talk as well as you can.
Let us finish the question
your question was, you had a doubt about our definition of
I
RS.
just was in the middle of my question.
No, let us finish the question.
If I take simple electrons, okay,
Yeah.
and I attribute the spin that grows and goes to infinity, then is a way of taking the bosons, okay? But if I use your definition, any finite RS for the fermions with spin up to 1 half will go in an infinite RS for the fermions with spin going to infinity, because we are degeneracy in the denominator. Because the kinetic energy, the average kinetic energy goes to 0. Okay. So I'm sorry, but the bosonic pool of particles have properties which are not so different from the normal electron gas. So I have the impression that your estimate of RS is very optimistic, and then the real coupling is not that one.
Okay, my response to that was that in all cases where we're predicting, comparing with a physical sample, we always present our results in terms of density. The RS is always an intermediate parameter.
Okay, Antonio?
Yes, one of the ingredients that you showed that in order to see this high critical temperature is that the fact that you have some, if you are close to some Van Hoek singularity, so you have some enhancement of density of states.
I don't want to interrupt before you give me the question, but it was just an observation that if you look at the density of states, you see a big boost.
Yeah, that's clear. No, my question is that when you have a really big boost of the density of the states, typically the system doesn't like that. So if you do experiments, usually the system avoids this Van Hoff singularity. So even though you do, you compute analytically and then you get this expression, of course you get that enhancement.
Yeah.
But sometimes there is some enhancement, but the system tends to change the lattice structure, the band structure, something in order to avoid this, because we cannot handle so much density of electrons. This is just my only
I think that, it's a valid question. I mean, you appreciate how we did the calculation, whether the system would in fact respond in the presence of that. It's a good point. We have not included, clearly have not included.
Actually, it's difficult to include because actually this is sort of experimental thing. So
certainly, no,
So one question here and another then Gordon, please.
Due to my ignorance, I have several questions that you can talk later.
Yes,
So the first question that I wanted to ask is, would there be other competing ground states? How do we know that this is the ground state?
That's a good question.
Well, that's a good question, but I think the only, just instinctively, the way I would answer it is this pairing, particularly in the BEC region, is so robust that I think it probably would be. That's not a very good answer, but I'm impressed with how robust is the attraction between the electrons and holes. So it's a Coulomb attraction, and then particularly in the BEC region, the pairs are compact. What are they going to do? They're going to Bose-Einstein condense. You know, unless something very subtle happens.
Yeah, it's a zero temperature cancellation.
Yes. Yeah, certainly. Yeah. So then one has to, of course, and in 2D it's challenging. One has to look at the determination of the transition temperature. And it is certainly true that if the zero temperature gap and so on is big, that does not necessarily indicate large transition temperatures. But I would say the converse. If you don't get a large if you don't get a large gap, you're not going to get a large transition temperature. Yeah.
Okay. Last question by Gordon.
You wrote down pictures for the screening of the GG and
Yeah.
Does that obey the F-sum rule?
I believe it does. Yes, it does obey the F-sum rule. If you do the full screening.
Are there vertex corrections?
It should be included.
There should be. There should be vertex
No, the
corrections.
diagrammatic structure, the real diagrammatic structure is very complicated.
But does the F-sum rule? I don't think the vertex corrections does that come in at the F-sum rule level? Does it? I mean, I know it comes in for the conservation of number, but I think it does come in the F-sum rule as well. Part of our. I mean, there's been a lot of discussion on this. Although. The fact that our screening result agrees with the unscreened case for almost the entire range. It's only just in this onset region that you get a difference. If you're in the unscreened case, of course, there's no screening, there's no issues of right. So that's that kind of, again, it gives you a robustness to the calculation. Yeah.
Okay. I think we need to move to the next speaker. Thanks, David, and thanks to all the questions. So now we have